The equivalence principle led Einstein to the position that the presence of matter curved spacetime, and that a body, free from all forces, travels geodesics in this curved space. With Riemannian geometry and the Ricci tensor, he had what he needed to develop the curvature side of the equation. First, we fixed the generalized n-dimensional coordinates to our 4 spacetime coordinates. The convention is for numbers to run from 0 to 3, with 0 being the index for the time coordinate. Then we find the volume of the 3 spatial dimensions for a given time dimension. This is the Einstein tensor. Physically, this tensor determines how the volume of a small group of particles in free fall along geodesics will change. Our little geodesic experiment helps illustrate this important fact. Here we see the change in the volume as the particles diverge and converge along various geodesics. This changes the shape of the volume from a sphere to an ellipsoid, but the total volume remained unchanged. The Einstein tensor is 0, even as the curvature of the space is not 0. By the way, this sphere to ellipsoid phenomenon is called a tidal effect, because it is how the moon creates tides on the Earth. In Newtonian physics, the force of gravity was created by mass, or more precisely, mass density, the amount of mass per unit volume. In general relativity, we need to change this from mass density to energy density, because of the equivalence between mass and energy, and to take into account the motion or kinetic energy of the masses. So in addition to calculating the mass-energy density of a volume of space, we need to account for the flow of energy through each surface of the volume. This information can be packed into a 4x4 matrix known as the energy-momentum tensor, or stress-energy tensor. Each element represents the flow of momentum across a surface. The first component represents classical energy density at a constant time. This was the only component used in Newton's equations. Similarly, the rest of the top row and left column is the energy flow across each surface. The rest are momentum flows across surfaces. For example, T12 keeps track of the flow in the x direction of momentum in the y direction. These are caused by pressure and stress at each surface. The final step for the gravitational field equations is to determine the constant of proportionality between the Einstein tensor that encapsulates curvature volume and the energy-momentum tensor that encapsulates the total energy density. We use the boundary condition that the equations must produce Newton's equations for spaces with very little curvature. You can see that this is a very small number. What this means is that it takes an enormous amount of matter and energy to produce even a tiny amount of curvature in the space around it. This looks simple enough, but because they're tensors, it represents 40 equations with 40 unknowns. These are the Einstein field equations for general relativity. We'll go over what they predict for gravitational phenomena near the Earth, near the Sun, and around a black hole in our next segment.
Hello, today we're going to be talking about the Bose-Einstein condensate. Now for those of you who really know what you're doing already, here's the short version. Once upon a time, wave functions. If antisymmetric under exchange, then fermions, and when very cold, Pauli exclusion principle. However, if symmetric, then bosons and Bose-Einstein condensate, the end.
Kevin, you can't do that!
Wait.
Sorry about that. In case you're not quite up to Kevin's speed, we'll elaborate a bit. So what is a Bose-Einstein condensate? When we cool a substance down until it's really, really cold, a Bose-Einstein condensate is one of the possible outcomes. This means that to understand a Bose-Einstein condensate, we need to examine exactly how matter cools. So what exactly happens when we cool stuff? When particles are cooled, they lose heat, which means that they vibrate more and more slowly as they lose thermal energy. As they cool, the atoms cluster closer and closer together. Imagine a waddle of penguins, or a bumper car ride. The more slowly the individual particles move, the less space there will be between them. In our case, the question is, how close together can they move? Can they all pile into the exact same spot, or is there some minimum distance that will always separate them? Oddly, both are correct, but they apply to two different types of particles. The easiest way to identify these types is by looking at whether they obey the Pauli exclusion principle, which says that no particles in the same state can occupy the same point in space. The first type of particle, known as a fermion, obeys the Pauli exclusion principle. This means that only a small number of them can be in the same place simultaneously. The other type, which does not obey this principle, is called a boson, and an infinite number of them can therefore all pile into the exact same place at once. Bosons are much more interesting for us, because these are what form the Bose-Einstein condensate. Some examples of bosons are the element isotopes helium-4 and rubidium-89, and non-atomic particles such as photons. Therefore, if we cool any of these particles down to low enough temperatures, we should observe the formation of a Bose-Einstein condensate. The resulting problem is how one goes about cooling particles down to several billionths of a Kelvin, because no traditional method of cooling will do the trick.
So one asks, how do you cool something down to the point of forming a Bose-Einstein condensate? The solution here is using a laser. The sample is loaded onto a so-called laser trap that has lasers pointing at the sample from each of the 6 coordinate axes. The lasers are tuned so that the wavelength of the beams are slightly longer than the electronic transitions of the atom. So as the atom moves towards the beam, the Doppler effect takes into effect by causing the beam to appear slightly more blue to the atom, causing the wavelength of the beam to appear shortened, and will be at the exact energy level necessary of an electronic transition.
Hey, can anyone explain to me why I just woke up stuffed into a closet down the hall?
Don't worry about that right now. Now that you're awake...
No, now that you're here, he means.
Oh, yeah, now that you're here, why don't you just help us in explaining laser cooling?
So now we have an atom that's sitting in a laser trap with laser beam pointing at it from all sides. How exactly does this cause the atom to cool down? Well, let's imagine that we're on the atom itself, looking outwards. If the atom moves in any direction, the beam will look a little bluer because of the Doppler shift, and the atom will be able to absorb a photon. Photons have momentum, and so in order to preserve momentum, the atom has to recoil in the other direction. Kind of like if you shot a little gun at it. Pew, pew, pew! Now eventually, this absorbed photon has to be re-emitted, but it's emitted in a random direction. And so, if the atom is absorbing many photons from one direction and re-emitting them all in random directions, the net effect is to slow down its motion in that direction. By using this technique, we can actually cool atoms down to very, very cold temperatures, sometimes within a few microkelvin of absolute zero. Unfortunately, the photon re-emission after the absorption defines a limit on how cold we can get the atom. Once the atom's motion is caused only by these random photon re-emissions, it is no longer possible to cool the atoms via this so-called Doppler cooling. So Doppler cooling is incredibly useful and incredibly fast. We can actually cool things from room temperature to a couple of microkelvin on the order of seconds. Unfortunately, it's still not quite good enough to get us to the temperatures needed for a Bose-Einstein condensate. So what do we do from here? We use the exact same mechanism that you've probably used to cool yourself on a hot day: evaporation. In our collection of ultra-cold atoms, some atoms will still have more thermal energy than others. By allowing the high-energy atoms to escape, we can lower the energy of the remaining atoms even further. Eventually, the energy of the leftover atoms becomes so low that they all coalesce to form a giant ball of wiggling, jiggling stuff. This blob of stuff, which contains hundreds of thousands of atoms piled on top of each other, is what we call the Bose-Einstein condensate.
This method of cooling that Kevin has just described so elegantly was employed by researchers in 1995 to produce the first ever Bose-Einstein condensate, 71 years after Bose and Einstein first predicted their existence. The first Bose-Einstein condensate of photons was made less than 2 years ago, which reminds us just how recently we've been able to observe this phenomenon. In the future, these types of breakthroughs may have practical outcomes and lead to a much deeper understanding of the quantum effects that govern our world. Currently, however, they mostly serve as a time-consuming pursuit for the intellectually curious, for those who see the Bose-Einstein condensates as exactly the type of classical rule-breaking anomaly that makes exploration into the world of quantum mechanics so freaking cool.
Pathological monsters, cried the terrified mathematician. Every one of them is a splinter in my eye. I hate the Dino space in the Cope curve. I fear the Cantor-Turner reset. The Sierpinski gasket makes me wanna cry.